Good morning, Math A. This is Miss Espinoza. Today we're not going to do lesson 7.2c. Instead, we're going to walk through the homework for 7.c. I think it's a little better of a learning setup. So here we go. If you have your PDF printed out, or if you're doing it electronically, or you have a piece of paper, so get set up if you're not set up, and then continue going on. For each of the following problems, find the necessary measurement to answer all the questions. A mini cereal box has the following dimensions: 4.5 inches by 6 inches by 2 inches. A, if all dimensions were doubled, will it require double the amount of cardboard to make the box? So I have to think, if I'm doubling the dimensions, that's talking about scale factor. But if I'm doubling the amount of cardboard, that's talking about area. So we think back to what we learned before. If our scale factor is A to B, then our area ratio would be A squared to B squared. So if in this instance I doubled the sides, that would make it 2 to 1 of what it was before. I would not be using twice the cardboard. I have to use 4 times as much cardboard. So here we would write no. It will not double the cardboard. It'll make the cardboard 4 times as much. So no. It would require quadruple the amount of cardboard. Okay. B, if all the dimensions were doubled, will it hold double the amount of cereal? So now we're talking about scale factor again, and we know if the scale factor is A to B. Then it's talking about holding the amount of cereal. Well, that's volume. Volume is not one-dimensional, it is three-dimensional. The volume would be A cubed to B cubed. So if we were to make the dimensions doubled, that'd be 2 to 1 here. Our volume would not be doubled, it would be 8 times as much. So no, it would hold 8 times as much cereal. Okay, so we always want to talk about what dimension we're in. If we're talking about sides, we're talking about one-dimensional because we're talking about length. If we're talking about area, we're two-dimensional. We're going to have to square our dimensions. If we're talking about volume, we're three-dimensional. So we always have to know those different dimensions. Okay, on C. If one dimension was doubled, will it require the same amount of cardboard to make the box? All right, well, let's just kind of look at how we would do this. So the original cardboard, we'll write original. Maybe if my pen will work, we'll write original. No, it is not working. Okay, I'll go use this pen instead. Okay, so here, my original, if I wanted to do my cardboard, that would be surface area. So I'd have 2 squares that were the 4.5 by 6. And I would have 2 squares that would be the 4.5, 2 rectangles, 4.5 by 2. And I'd have 2 rectangles that would be, what other combination did I not put together? Let's see, I put 4.5 and 6 together. I haven't put 6 and 2 together. So 6 by 2. Okay, so if I went and calculated that, I would get 54 plus 18 plus 24, which would be 96. Now, if I only doubled one of the dimensions, then what would happen is I'd be doubling maybe the 4.5. So here, this would get times by 2, and over here, this would get times by 2, but nothing over here in this third one would get times by 2. So I would not be doubling all of the cardboard. So over here, I'm going to say no. One of the rectangles does not get a double dimension. I guess it's two of the faces. No. Two of the faces do not change. Again, if I doubled the dimension like the 4.5, these two faces would change, these two faces would change, but these other two faces would not change. So I wouldn't be enlarging the cardboard on those two sides. Okay? If one of the dimensions is doubled, will it hold double the amount of cereal? Again, so if I look at the original, I look at the volume. So I'll go look at volume. Volume, I'm doing the 3 dimensions, the length, the area, the base, times the height. So I'm multiplying the 3 numbers. And my original volume, 4.5 times 6 times 2, I get 54. Okay, now if I double one of the dimensions here, so if I go over here and maybe I double the 4.5, well then yes, I'm just making a times by 2 over here, and that would effectively times the 54. So yes, it would increase the volume by twice as much. Yes, because multiplying one dimension by 2 also multiplies the volume by 2. All right, next one. E, if all the dimensions were increased by 4 inches, so the 4.5 is turning into 8.5, and the 6 is turning into a 10, and the 2 is turning into 6, how does this change the amount of cardboard that's needed to make the box? Oh, it's just going to make it bigger. So our original over here, wow, I did not mean to do that. Let me undo. My original over there, I had, over here I added up to get to 96. I'm going to do the same thing, but I'm going to do it with my new dimensions, 8.5 by 10 by 6. Okay, so I'd have 2 for my surface area. I'd have 2 that were 8.5 by 10. And then again, I'd have 2 faces that were 8.5 by 6. And then I have 2 that were 10 by 4, 10 by 6. Okay, and then I would add that on up. And when I did that, here, 8.5 times 2 times 10, 170. 2 times 8.5 times 6, 102. Then I get 120. I get 392. So I added a lot more cardboard. Okay, I went from 96 inches squared all the way here to 392 inches squared. So the cardboard would increase. From 96 square inches to 392 square inches. Okay, next one. If all the dimensions were increased by a value of 4, as described in E, how will it change the volume? So how much cereal can hold, the volume. So I'm going to add 4 to each of these. So here we go. My volume. The 4.5 is an 8.5, the 6 turns into a 10, and the 2 turns into a 6. And we multiply that. We get 8.5 times 10 times 6. We have 510 inches cubed. So we went from 54 inches cubed to 510 inches cubed. The volume would go from 54 cubic inches to 510 cubic inches. It increased by a lot. Okay, there's not a fast way to do it when you're adding to the dimensions. There's a faster way to do it when you're multiplying your dimensions, but not when you're adding. When you're adding, you just have to take it all out. Okay, number 2, a container of chocolate milk has the following dimensions: a square base with sides of 6 and a height of 9. If all the dimensions were reduced by a scale factor of 1/3, will it require a third of the amount in the material to make the container? Okay, so the dimensions being reduced to scale factor. So in this problem, I know that the scale factor is 1 to 3. Okay, and then, because I saw dimensions, that's how I know it's scale factor. And then here, well, it's a third of the amount of materials. That is going to be surface area. So this is an area ratio. If the scale factor is 1 to 3, then I know that the area ratio has to be 1/3 squared, which is 1 to 9. So will it make a third? No, it will make a ninth. So no. We would need 1/9 of the material. Okay. If all the dimensions were reduced by a scale factor 1/3, would it hold a third amount of the chocolate mix? So again, the dimensions is telling us scale factor. Scale factor is 1 to 3. And holding the chocolate milk, that's a volume ratio. The volume ratio would be 1/3 cubed. So 3 times 3 times 3 is 27. So no, it wouldn't be a third of the chocolate milk. It would be 1/27 of the chocolate milk. No, it would hold 1/27 of the chocolate milk. Okay, see, if the dimensions of each were reduced by a scale factor of 1/3, but the height stays the same, what are the new dimensions? So this one we're just going to have to work out. So here, I'm going to go ahead and put the original. So originally I had a little rectangular prism, and it had a square base and a height of 9. So 6 by 6 by 9. And now my new shape, I still have a square or a rectangular prism. And it says the length of the base of each side would be reduced by a third. So 6 divided by 3 is 2. But the height will remain the same. So this is still going to be a 9. And now we have to figure it out. What are the new dimensions? Well, the dimensions are 2 by 2 by 9, as we just drew. 2 by 2 by 9. And I don't know which units we're in. We're in inches, so inches. Okay, what's the new surface area? Well, here I have 2 sides that are 2 by 2s. Again, I always use my 3 combinations. 2 sides that are 2 by 9s. Okay, so I think the 2 by 2s, that is taking care of the bottom and the top. one of the 2x9s is taking care of the front and the back. But then I have another 2x9, which is taking care of the right and the left. Okay, so we work it out. 2 times 2 times 2 is 8. 2 times 2 is 4, times 9 is 36. 2 times 2 is 4, times 9 is 36. 36 plus 36 is 72. 72 plus 8 is 80. So this would be 80 inches squared. Okay, volume of the reduced shape. Okay, so we just multiply the 3 dimensions. 2 times 2 times 9, that would get 36 inches cubed. All right, draw and describe a plane section that results from cutting a cylinder parallel to its base. Okay, so if I had a cylinder, I'll go ahead and draw a cylinder. Might not be beautiful. There we go. This is like from the ninja video you watched, right? And we're cutting parallel to its base. So we're chopping with our knife like that. I want to know what is the shape that would be cut. So when I look, the stamp that would be in my shape is a circle. So I would get a circle congruent to the base. Okay, Catherine is visiting patients in a hospital. She visits 9 patients in 3 hours. She visits 18 patients in 6 hours. Is this situation proportional? If so, what's the unit rate? Okay, so let's figure out how many patients per hour and see if it's the same. So 9 patients in 3 hours. Well, that's the same as seeing 3 patients 1 hour. And on the other one, we have 18 patients in 6 hours. We reduce that down. Yeah, that's again 3 patients in 1 hour. So is it proportional? Yes. Yeah. Whoa, where did my typing go? Who knows? Yes. It is proportional. She sees 3 patients per hour. Okay, that's the end of this one homework. And now you are going to log into our next lesson for 7.2D. So I will see you in a little bit in that lesson.